Okay, so this is another problem I'm doing out of Conquering the Physics GRE. Just trying to do more of these to get more practice and get better. And this one says a small puck of mass big M is attached to a massless string that's dropped through a hole in a platform as shown in the diagram above. The puck rotates at a radius r when the tension in the string is T. The string is pulled downward until the radius of rotation is r, little r, which is less than big R. What is the change in energy of the puck when the radius decreases? And you may assume the puck is a point mass. So the only type of energy we're going to have for this puck is the kinetic energy. And the change in kinetic energy is just your final kinetic energy minus your initial kinetic energy, which we know to be equal to 1/2 m, I'm going to call it just v squared, minus 1/2 mv initial squared. Now, obviously, if we look at our option choices, that's not an option. That's a little too easy. What we need to do is we need to relate mass and our velocity squared, the initial and the final, with our tension, our big radius, and our little radius, since those are all things in our equation. Now, I'm going to start by using angular momentum and the conservation of angular momentum, which is L final is equal to L initial. There's angular momentum is conserved. There's no external forces that would not allow that. And the other reason is it mentions it's a point mass. So we're probably going to use the fact that the inertia for a point mass, the moment of inertia, is mr squared. And the r is going to obviously depend on if we're looking at the initial or final, but we'll do that now. So this is going to be equal to I omega, which is equal to I omega initial. And like I said, for the point mass, the moment of inertia is going to be m times r squared. Now, for our final position, we know that it's going to be a radius r, and initially as a radius of big R. So I can say m little r squared omega is equal to m big R squared omega. I guess this is technically a capital M, right? And the masses will drop, and you get just r squared omega is equal to big R squared omega initial. And the next thing we need to know is that omega is equal to your velocity over your radius. This is the relationship between angular velocity and linear velocity. So again, the r is going to depend on when. So basically what happens is each term will drop because you'll have r squared v over r equal to r squared v initial over big R. So you end up just getting RV is equal to big R v initial. Or if you want to relate this in terms of, we can say that V naught is equal to RV over big R, just solving for our initial velocity. Okay, so that's something I needed. I needed V naught. Well, I needed MV, I suppose. Basically, we want these. And we have V naught now, which is good. Now, the next thing to consider is Newton's second, which says that the sum of all forces, in this case, we're going to have mass times the centripetal acceleration because it's rotating. And the only force we have is tension. So tension is equal to our centripetal acceleration, which is going to be V initial squared over big R. Now, I did that because when we read the question, it says the tension, when at the radius R, the tension in the string is T. So that's your initial condition, is basically what that's saying. So V initial and then big R. So that's obviously no problem. Now what can we do? Well, we know what V initial is, so I could plug that into here, right? So I can say tension then is equal to m little r squared final velocity squared over big R. And now notice I can solve for mv squared if I multiply over by big R and I divide over by the mass. Yeah, perfect. So notice you get mv. Oh, this should be cubed, right? Because when I square this, that'll be v squared, and we already had a v cubed, so this is actually cubed. R squared, little r squared, there we go. So we essentially squared this to get little r squared, v final squared over r squared, and we plug that in, we get m r squared, v squared, and this is r cubed because there's already an r here. And we're solving for mv squared. So that's actually going to go into this first part here. We now know what that is. Okay, so we have that. Now that we have that, we need to find basically your mv initial. So mv initial, we could have just looked right here because we know that t is equal to v initial squared, mv initial squared over big R. So this is just from here. Maybe I could even do it over there, so that makes more sense. Basically, we're not substituting. And we could say just t times R is equal to m v initial squared. Let me move this down because this is a pretty important part. So now we can substitute those into your kinetic energy. So you have 1/2 mv final, so t mv final squared, so t r cubed over little r squared minus 1/2 just t times r. And this is your change in kinetic energy. And then to make it look the way they have it, we can factor out a 1/2. They all have a t, and they all have at least one r. So I can factor out t times r, and I'll get big R squared over little r squared, and then minus 1, because that factors everything completely. And this is your change in kinetic energy. So if we look at our options, 1/2 t r, it's A, right? So that's essentially how we do that problem.